Hi, we are from Group 4 and we will present about internal energy. Let's start with the definition of internal energy. Internal energy is the energy associated with the random, disordered motion of molecules. The internal energy cannot be measured absolutely. Thermodynamics concerns changes in the internal energy, not its absolute value. The processes that change the internal energy are transfers into or out of the system of matter or of energy, as heat or by thermodynamic wake. The unit of energy in the international system of unit is the joule. The internal energy relative to the mass with unit joule per kg is the specific internal energy. The corresponding quantity relative to the amount of substances with unit joule per mole is the molar internal energy. U is the most common symbol used for internal energy. The molecules at a higher temperature move more rapidly than at lower temperatures. Hermann von Helmholtz is the one who developed the idea of internal energy, which is the total of a system's kinetic and potential energy, and proposed the principle of energy conservation. While Rudolf Clausius established the principle of energy conservation in thermodynamic processes, known as the first law of thermodynamics, the concept of internal energy has evolved significantly as a result of his work on the first rule of thermodynamics. The idea of internal energy underwent a major change in development during the 19th century. A system may include energy in a variety of forms, such as potential energy and kinetic energy related to temperature. Many people give Helmholtz credit for developing the idea of internal energy, which is the total of kinetic and potential energies, as well as for developing the principle of energy conservation. There are three theories of internal energy. First, internal energy is the energy contained in the random and disorganized motion of molecules. Second, when heat or work is applied to a substance, its internal energy is raised. Lastly, the internal energy of a system is the total of all microscopic energies. The internal energy of a system is a thermodynamic state function that represents the sum of all the energy in the system. Internal energy equations vary depending on the system and components involved, but they frequently can be stated as U equals to kinetic energy plus potential energy. The unit for internal energy is joule. Kinetic energy is the energy of motion, which can be seen as an object or subatomic particle moving. Formula for kinetic energy is 1 over 2 times mass times volume to the power of 2. While potential energy is the energy stored in an object as an effect of its position. To find potential energy, we use formula mass times gravity times height. For example, does a cup of hot coffee have internal energy? The answer is yes. The internal energy of the coffee is related to the kinetic energy of its individual molecules. As the coffee heats up, the molecules within it move faster and have higher kinetic energy. This increase in internal energy is what makes the coffee hot. When you touch the cup, you can feel the heat transferring from the coffee to your hand, which is the transfer of some of the internal energy of the coffee to your skin. So, in this example, the internal energy of the coffee represents the sum of the kinetic energy of its molecules, which manifests as its temperature and the sensation of heat you experience when you touch it. Next, does stirring a pot of soup increase the internal energy? The answer is yes. When you stir a pot of soup, you're adding mechanical energy to it. This mechanical energy increases the internal energy of the soup by agitating its molecules and increasing their kinetic energy, which can result in a more uniform temperature distribution in the soup. There are 3 forms of kinetic energy, which are translational, rotational, and vibrational. Let's move on to examples of calculations using a 2 kg object located 5 meters above the ground. Calculate the internal energy of the object when it is at rest at this height. Let's see the solution. The value of kinetic energy is 0 because it is at rest. Then, we find the value of potential energy by using the formula. Then substitute the value into the formula of internal energy. Thus, we will get the answer, which is 98.1 joule. Next, the 2 kg object is falling and reaching 3 meters per second at mid-air. Calculate the potential energy at the moment if total internal energy is same as in question 1. Based on the formula of internal energy, we can find the value of potential energy. Thus, potential energy equals to internal energy minus kinetic energy. We substitute the value given in the question into the formula. Thus, the final answer is 89.1 joule. This is how we plot the graph for question 1 using the MATLAB. The bar graph shows energy versus object. At rest, kinetic energy 0 joule, potential energy 98.1 joule, and internal energy 98.1 joule. This is how we plot the graph for question 2. The bar graph shows energy versus object. At midair, kinetic energy is 9 joule, potential energy is 89.1 joule, and internal energy is 98.1 joule. Lastly, these are the references that we used to make this video. That's all from us. Thank you.